I now want to talk about key modes of paleoclimate variability. What I mean with key modes are key cycles. A cycle is something that repeats. You can imagine that you have a warm phase and a cold phase. So you're living in a warm phase for a certain period of time, and then the warm phase turns into a cold phase. Again, over approximately the same period of time, and then it swings back. Okay, this is what we call key modes. And the key modes of paleoclimate variability have different time scales. And let's talk about time scales. Okay. So here is a graph that tries to illustrate different time scales, and it also shows the time scales of key patterns of variability. One is known as ice age cycles. Okay? And the time scale of ice age cycles is 50,000 years. And the other key mode of variability are hothouse icehouse cycles, shown up here. And the period of these cycles is 50 million years. So now, how do you understand these different time scales? This is a little bit tricky. So what I did is I created here the baseline of my sketch, and I used a unit of 500 years. So this is 500 years here. If you multiply it by 10, you get a time scale of 5,000 years. Okay? If you multiply this by 10, you come to 50,000 years, which is the time scale of ice age cycles. Okay? What it means is, in an ice age cycle, you live in a relatively warm phase for 50,000 years, and then it turns into a relatively cold phase for the next 50,000 years. It's a long time. We're talking about very, very long times here. Okay? Relatively long times. Okay? So if you now look at it at an ice age cycle and you multiply it by 10, you ending up in 5 million years, you multiply it by 10, 50 million years, and this is the time scale of hothouse icehouse cycles, 50 million years. And hothouse icehouse cycles are the most extreme climate conditions that you can have on Earth. Okay, and you can be in a hothouse cycle for 50 million years, or you're afterwards in an icehouse cycle for approximately the same time. And so now, to understand these climate extremes, let us focus first on hothouse icehouse cycles. Okay, so you have two extreme phases. The warmest condition you can have on Earth is what we call a hothouse. No ice, warm in most regions, or in all regions. No sub-zero temperatures. That's what we call the icehouse, the hothouse. And then we're coming to the icehouse, where we have a large extent of ice coverage. Okay, the ice extending towards the equator. Okay, that's what we call the icehouse. And what controls the climates of these two extreme events? Okay, the hothouse is controlled by high CO2 concentrations, the greenhouse gas effect. The ice house is controlled by a large extent of ice by the cooling effect due to the reflection of solar radiation. We call this albedo. You'll learn more about the greenhouse effect and the albedo effect in future lectures. But imagine that you have these two extremes, noting that the conditions near the equator might actually be the same. Okay, you might have similar conditions near the equator because the Earth actually extends from the polar regions, might reach into mid-latitudes, might reach into subtropical regions. Okay, but not necessarily the equator. So imagine that you have these two extreme phases. You can be in a hothouse or in an icehouse, but in addition, on these very long time scales, you also have the continental drift. So a specific location on a continent, actually on these long time scales, might drift from the equator into colder climates, into mid-latitudes, or the other way around. So if you interpret a long-term time series of climate proxies, you have to take into account for this continental drift. Okay, let's have a little bit more detail of how does the temperature distribution look like on Earth. Okay, in these different climatic conditions. And this is a very busy graph here, and I will spend a little bit more time explaining what is shown. So, first of all, these curves show you the temperature distributions from the South Pole across the equator to the North Pole. And each curve corresponds to a different climate. Okay? Distribution from the South Pole to the North Pole. And the vertical axis shows you the temperature. Okay, gives you the scale. It's a little bit hard to read, that's why I tell you what it is. It starts with 30 degrees, is here shown at the maximum. It's the maximum range shown. 20 degrees, 10 degrees. The horizontal line here is the 0 degrees Celsius. So you get to freezing conditions, -10, -20, -30 if you go down. Okay, so for each curve, there are numbered the curves from 1 to 7. You can see on the left side. And in this table which is shown here, it tells you the temperature at the pole for each case. Okay. There's more. There's on the right side, it tells you also what is the global mean temperature for each case. The global mean temperature. So let's just have a look at one extreme condition. The extreme hothouse is this topmost curve, and the extreme hothouse has a temperature of plus 13 degrees Celsius at the pole. At the equator, there is no difference. It's around 25 degrees Celsius. All scenarios have the same temperatures at the equator. Okay? All right, the global mean temperature for that extreme hothouse climate is 23 degrees Celsius. And you can compare that to the current climate that we have, which has a global mean temperature of plus 15 degrees Celsius. Okay? So in this situation, there's temperatures above zero everywhere, no ice. No ice coverage, no ice at the poles. Okay? So now let's have a look at the other extreme, the so-called severe hothouse, number 7. And in this situation, you can read here that the temperature at the poles is minus 50 degrees Celsius. You have a negative temperatures until you reach a geographical latitude of something around 55 degrees south. Then it turns positive temperatures and turns into negative again at 55 degrees north, turning into, and the global mean temperature is 12.5 degrees Celsius. Okay, and we currently are living in that situation, which is number 6 here. We are around 15 degrees Celsius global mean temperature. Okay, these are the extremes. It's a theory, but it's sort of based on, and it fits with the global observations. This has been suggested by Scott Thiese in 2016, so it's not that old, that theory, but that's the basis of trying to understand the climate proxy data. Okay, so what are the assumptions? Just to repeat, equatorial zones remain largely unaffected by climate changes. Warming, cooling effects pronounced at higher latitudes due to glaciation effects and associated climate feedbacks, and the global mean temperature varies between 12.5 and 23 degrees Celsius. And now you can draw a timeline of events, of transitions. And let's see how it looks like. This is how the timeline looks like. Okay, you can see the different periods are shown here. Okay, from the past to today. Today is on the right. And you can see transitions between extreme cold to extreme warm. Okay, try to get the mouse working here. From extreme cold to extreme warm. Okay, and back, you can see sometimes the cold phases are a little bit shorter. Okay, you get this. And actually these the transitions between cold and warm actually tend to agree with the timing of mass extinction events on Earth. And you already learned that these are linked to global cooling and warming events. Okay, so this is really what are the hothouse and icehouse cycles are about. And scientists were able to reconstruct these cycles. Okay, and you learn about the absolute extremes of climates that we can have on Earth. Okay, and each extreme, okay, or the transition actually is associated with mass extinctions. You can also see that currently we actually live in a relatively cold climate, but we are in a very rapid transitions into a warmer climate caused by human actions, okay, caused by the release of CO2. So I also want to mention the so-called snowball Earth case. Okay. Because there has been the suggestion that, which is a little variation to the theory that I just presented, that maybe the ice coverage also included equatorial regions. Maybe the entire Earth was covered during icehouse climate. So the snowball Earth hypothesis proposes that during one or more of the Earth's icehouse climates, the planet's surface became entirely or nearly entirely frozen. Okay, there is no evidence for that, for this suggestion, but maybe it was the case. And the 5 stages of snowball Earth are actually shown here. Okay, and these transitions are actually linked to what we call climate feedback mechanisms. Okay, so the transition from an ice-free to an ice-covered Earth maybe you can link that to something that we know as the albedo feedback. Okay, because you start having ice cover, the ice reflects solar radiation, leads to a cooling effect, you get more ice and the ice extends even further, you get more cooling, and it's a feedback mechanism that creates more and more ice on very, very long time scales. The opposite phase is triggered by a release of enormous amounts of CO2, maybe trapped underneath the ice. You know, a trap of CO2 outgassed by volcanoes, by the buildup of albenos. The volcano buildup. Okay, that's a cycle. Think about that. You know, we learn quite a bit from, you know, trying to understand these past climate changes. Okay, now you can have a little break. You know, maybe hit the pause button, because I want to talk about shorter time scales of ice age cycles. So let's have a look at that. This is from ice cores, you know, from ice core data over the past 800,000 years. Okay. So let's have a look. If these are reconstructed temperature data, let's have a look at it. And it's in terms of temperature anomalies in degrees Celsius, and the time scales, not the time scales, the scale of temperature anomalies is about up to 10 degrees Celsius. Okay, and we're talking about polar temperatures. We're not talking about equatorial temperatures, only polar regions, okay? Maybe extending into subpolar regions. Okay, and we have times where the climate was cold, known as ice ages, maybe for up to 100,000 years, yeah, between 50 to 100,000 years, and we had times where it was warmer, known as warm interglacials. Okay, and we had these transitions between ice ages and warm interglacials. Okay, so now how can you imagine that in the context of these ice house and hothouse cycles? Well, these events are not as extreme, the ice ages. This is a reconstruction of how the last glacial maximum looked like in terms of the ice coverage, and you can see that there is an ice coverage spreading more into the mid-latitudes in North America, you know, and you almost reaching the Mediterranean region here, you know, and that's, you know, it's not ice coverage of the entire planet, but it's a more extensive ice coverage of reaching into the mid-latitudes. Okay. In addition, okay, and I probably should have mentioned that a little bit earlier, the cooling and warming phases are always linked with changes of the sea level. Okay. The warming phase, because seawater expands, so if you warm it, it expands, and the only way it can really expand is upward, you know, because it's constrained by confined by continents. Okay, and also the melt of glaciers contributes to the sea level rise. Okay, and during cooling event, it actually becomes compressed. Okay, the sea level drops. All right. I mean, that's what we're talking about. These climate variations, they are not as extreme. Okay, because you noticed that the temperature variations are much bigger during the hothouse and icehouse cycles. but these ones are also significant climate variation, and I will discuss the reasons for these climate variations during the ice age cycles in a separate lecture. Okay, and just to mention that there are also much shorter events of temperature variations in polar regions, which are in the northern hemisphere, which are known as Dansgaard-Oeschger events or DO events. And these events occurred 25 times during the last glacial period. Okay, and we know that because we can resolve much higher timescales in ice cores. In the northern hemisphere, they take the form of rapid warming episodes, typically in the matter of decades, each followed by a gradual cooling over a longer period. For example, about 11,500 years ago, average annual temperatures on the Greenland ice sheet increased by around 8 degrees Celsius over 40 years in 3 steps of 5 years, whereas a 5 degree Celsius change over 30-40 years is more common. And these DO events are caused by climate feedback mechanisms at high latitudes that I'm not going to discuss. And there's some little evidence here over my shown in this graph of rapid temperature changes. Okay, and these temperature changes are regional on the regional scale. They're not global events. They are regional scale events that happen on relatively short time scales. So what have you learned? Well, here are some study questions. So where on Earth do we get the least climate variations? Okay. What are the key modes of climate variability on geological timescales? What are hothouse icehouse cycles? What are ice ages? What's the time scale of ice ages? What are the general causes of mass extinction events? What does snowball Earth refer to? And what are Dansgaard-Oeschger events? So, thank you very much. I hope that you enjoyed this lecture, and if you have questions, please send me an email. Okay, thank you.